Ever wondered what actually makes code fast? I bet the answer isn't what you think. It's kind of like one of the best-kept secrets in all of programming. So let's dive in and uncover it together. Okay, so get this. This is the big mystery, right? The one question that really separates the pros from the amateurs. How in the world can 5 lines of code be slower than 100 lines? It just doesn't make sense. It feels totally backward, but I promise you, it's absolutely true. And here's the paradox right in front of you. On one side, you've got this tiny little loop. On the other, a long list of instructions. Now the secret? It has nothing to do with how many lines of code you're looking at. The real culprit is that little letter N over there. You see it? That represents your input size. And believe me, the whole game changes depending on how much data you throw at that loop. It's all about how your code scales. So what we're really bumping up against here is what I like to call the code speed illusion. It's this trap we all fall into, thinking that fewer lines of code automatically means faster code. Well, today we're going to pull back the curtain and show you the secret language that reveals the real story behind code efficiency. And that secret language? It's called Big O notation. Now, I know, it sounds super academic and maybe a little intimidating, but don't worry. At its core, it's just a really simple way of talking about how complicated an algorithm is. All it does is answer one simple question. As our input, that N, gets bigger and bigger, what happens to our performance? And listen, this next part is absolutely crucial. When we talk about Big O, we completely ignore the hardware. It doesn't matter if you're running on a brand new supercomputer or a laptop from 2010. We're not measuring time in seconds. Nope. We are counting the number of fundamental steps the code has to take. Think of it like a recipe. We care about the number of steps, not how fast your oven is. Okay, so how do we actually use this secret language? It might look complicated from the outside, but it really just boils down to a few super simple rules. Seriously, think of it like a decoder ring for your code. You ready? Let's start cracking the Big O code. Here they are, the 3 simple rules that unlock everything. Rule 1, drop the constants. Rule 2, find the most dominant term. And Rule 3, always, and I mean always, focus on the worst case scenario. Let's break each one down. All right, rule number 1, ignore the constants. So let's say your code takes, 5 n steps to run. In the world of Big O, we just say it takes n steps. Why? Well, think about it. When n is a billion, does that little 5 out front really matter? No way. The explosive growth is all coming from n. So to keep things simple, we just drop the constant. Rule number 2, the strongest term wins. Okay, picture your code has 2 different things happening. One part takes n squared steps and the other part just takes n steps. Well, as that n gets bigger and bigger, the n squared part becomes this absolute monster. It just completely dwarfs the other n term, making it look insignificant. It totally dominates. So just like with constants, we drop the weaker, lower order terms. And this little chart here shows you exactly what I'm talking about. This is the power ranking. Up at the top, you've got O of 1. That's your rocket ship blazing fast. Then you've got O of n, which is, it's fine, it's okay. But then you get down to O of n squared. That's the danger zone. That is the kind of dominant term that can bring your entire program to a screeching halt. Okay, that's enough theory for now. Let's get our hands dirty and see how this actually works with real code. We're going to look at 3 different levels of efficiency to see these rules in action. First up, level 1, constant time. This is the dream, folks. No matter what you throw at this code, it does the exact same number of things. Its runtime doesn't care about the input size n at all. You could give it 1 piece of data or a billion pieces of data. The number of steps it takes stays the same. It's fixed. And in Big O speak, we call this O of 1. Now, the 1 here is a bit tricky. It doesn't mean it takes literally 1 step. It just means the number of steps is constant. It could be 3 steps, it could be 10 steps, but remember our first rule? We drop the constants. So it all just gets simplified down to O of 1. All right, moving on to level 2, linear time. And this is the home of the good old for loop that we all know and love. With this, the performance is tied directly to the size of your input n. Super simple. If n is 10, you do about 10 bits of work. If n is 1,000,000, you do 1,000,000 bits of work. It's a straight, predictable line. And yep, you guessed it, we call this ON. As your input gets bigger, the work it has to do grows right along with it. This is probably the most common one you'll see, and honestly, a lot of the time, it's perfectly fine. And now, we've arrived at level 3, quadratic time. Okay, this is where things can get pretty scary.
This is where you have a loop stuck inside another loop. And what that means is for every single time that outer loop runs, you have to run the entire inner loop all over again. The work doesn't just grow, it explodes. Which brings us to the villain of our story, O of n squared. See, if your input n is just 10, it does 100 steps. No big deal, right? But what if n is 10,000? All of a sudden, you're looking at 100 million steps. This is the kind of stuff that can bring a whole system crashing down.
Okay, pop quiz time. Let's say you've got a piece of code with an if-else statement. The if part is pretty fast. It runs in O of n. But the else part, well, that's our slow O of n squared villain. So the question is, what's the big O for the whole thing? Which one do we pick? And that brings us to our third and final rule. Always plan for the worst. When we're using big O, we are professional pessimists. We always look at the absolute worst case scenario. We have to assume that the slowest possible path is the one that's going to get taken. So that whole block of code is defined by its slowest part, its O n squared.
Okay, so you get it now, right? Drop constants, find the dominant term, plan for the worst. It seems like you're all set to analyze any algorithm that comes your way. But hold on a second. There's one last really important twist that every great developer needs to understand. And here it is. After all that time I just spent telling you to ignore constants, in the real world, constants can absolutely matter. See, the rules of Big O are an amazing guide for understanding how things perform at a massive scale, but they aren't the whole story. I mean, just think about it for a second. Most of the apps we build aren't dealing with a trillion pieces of data, right? If your input size n is usually around, say, 100, then an algorithm with a really big constant might actually be slower than one that looks worse on paper with Big O. You've got to balance that theoretical worst case with the average case that your users actually experience every day. A real, tangible 2x speed improvement for them right now is way more valuable than trying to solve a theoretical problem you might never even face. So, here's the bottom line. Understanding Big O is about knowing how code behaves when you push it to infinity. But true wisdom, that comes from knowing how it behaves for your users with your data. So the real question isn't just about knowing the rules, it's about knowing when it's actually smart to break them.